In a groundbreaking study, researchers propose a novel tri-modal architecture that integrates large language models, LLMs, into a multimodal framework for automated depression classification from clinical interview recordings. This research addresses the significant limitations of prevailing diagnosis methods for major depressive disorder, MDD, which affects over 300 million individuals globally. The proposed architecture leverages ILM's ability to learn from large corpora to effectively process text data and potentially improve depression diagnosis accuracy. It consists of Mel Frequency Cepstral Coefficients, MFCCs, facial action units, FAS, and a two-shot learning-based GPT-4 model to process text data. This is the first work to integrate LLMs into a multimodal architecture for this task. The authors present impressive results on the DAIC-WOZ AVEC 2016 challenge cross-validation split and leave one subject out. LOSO, cross-validation split. The proposed architecture surpasses all baseline models and multiple state-of-the-art models, achieving an accuracy of 91.01%, an F1 score of 85.95%, a precision of 80%, and a recall of 92.86% in LOSO testing. This work contributes to the field by proposing a novel tri-modal architecture that incorporates LLMs for depression diagnosis, demonstrating the effectiveness of LLMs in multimodal architectures, and integrating the proposed architecture into a locally hosted web application to emulate real-world use. The study also provides an overview of related works, specifically discussing the use of MFCCs in audio-based models for diagnosing depression and other psychiatric disorders. These works establish the importance of audio data in diagnosing mental health conditions and demonstrate the need for multimodal approaches that incorporate other data modalities, such as text and video. The authors draw upon previous studies that have compared the effectiveness of various audio data representations, including MFCCs, for diagnosing depression from clinical interview recordings. They highlight the significance of MFCCs as a feature extraction method for audio data and establish the foundation for their proposed architecture. Multimodal fusion systems have emerged as a promising approach for binary depression classification, leveraging the strengths of various modalities to improve overall performance. These systems predominantly combine audio and video features, with some incorporating text features as well. Audio features, such as Mel Frequency Cepstral Coefficients, MFCCs, are widely used due to their effectiveness in distinguishing between depressed and non-depressed patients. MFCCs provide a compact representation of the human perception of sound, and certain coefficients follow a consistent pattern present only in depressed patients. Facial action units, FAS, are commonly used video features in these models. FAS represent low-level facial muscle movements, allowing for the objective study of facial expressions and nonverbal cues. A subset of 20 out of 44 total FAS is typically used in these models. Most state-of-the-art models for depression diagnosis from clinical interview recordings consider at least audio and video data. Multimodal models combine both verbal and nonverbal cues to reach a diagnosis, leveraging the strengths of each modality to enhance overall performance. The use of multimodal fusion systems has been shown to outperform single-modal systems. For instance, the work by Othmani et al. Achieved an accuracy of 87.40% using a CNN model with late fusion of audio and video features. Similarly, the work by Ceccarelli et al. Achieved an F1 score of 87 using a BiLSTM model with late fusion of audio and video features. The importance of using a combination of modalities is underscored by the fact that no single modality has been found to be sufficient for accurate depression diagnosis. Multimodal fusion systems allow for the leveraging of the strengths of each modality, leading to improved overall performance. The proposed approach for multimodal depression diagnosis will be discussed in the next section, building on the insights gained from the analysis of existing works. Multimodal depression diagnosis from clinical interviews relies on effective fusion strategies and data collection and preprocessing methods. Three primary fusion strategies are employed: early fusion, late fusion, and model-level fusion. Early fusion involves concatenating representations of different modalities before feeding them into a neural network, which can lead to the curse of dimensionality. In contrast, Late fusion processes individual modalities separately and then concatenates their outputs for a final decision. Model-level fusion, the most commonly used and best-performing strategy, combines these two approaches by processing individual modalities before concatenation and further processing the combined data to reach an output. The DAIC-WOZ dataset, containing 189 clinical interviews ranging from 733 minutes, is utilized in this study. Each interview includes a 16 kHz wave recording, a CSV text transcript, an ID numbered 300492, and features collected from video data. The dataset provides 6 visual features extracted using the Open Face Pose Estimation Library, with only the facial action units, FAS, considered in this study. Depression is assessed using the SHRI, Patient Health Questionnaire 8, PHQ-8, which measures 8 items on a scale of 0 to 3 based on how often problems have been occurring over a 2-week period. A cutoff score of 10 is used for the binary label, where participants scoring higher are considered depressed. Prior to pre-processing, several errors in the DAIC-WOZ dataset were identified and resolved, including removing interactions between research assistants, interruptions, missing therapist utterances, out-of-sync transcriptions, and labeling errors. Text pre-processing involved fixing these errors using regex and NLP techniques to make the text suitable for analysis. The pre-processing steps applied to the DAIC-WOZ dataset are visualized in Figure 3. To enhance the quality of the data for input into a large language model, LLM, it was necessary to address unique identifiers, acronyms, grammatical errors, and non-speech elements present in the original transcripts, Table 2. Unique identifiers, generated by automatic transcriptions, were replaced with their true meanings using regular expressions, regex. A Python dictionary was created to extend acronyms into their full forms. Non-speech elements, such as coughing, and cut-off speech were removed using regex. Grammatical accuracy is crucial for classification accuracy in LLMs. However, the DAIC-WOZ transcripts contain significant grammatical errors. The T5 base grammar correction model was applied to correct punctuation and capitalization. A support vector machine was trained to identify interrogative sentences and apply punctuation accordingly, achieving an accuracy of 97%. Speaker names were adjusted to provide context and clarify roles in the conversation. Ellie was replaced with therapist, and participant was replaced with patient. Following these corrections, subsequent utterances by the same speaker were merged. The resulting transcripts were converted into raw text data, with subsequent utterances separated by new lines and speakers diarized using their names followed by a colon. Audio pre-processing involved 4 stages. First, audio was segmented to include only patient speech, using timestamps from the transcript. Second, audio data was augmented to increase the number of samples by a factor of 7. Third, Mel Frequency Cepstral Coefficients, MFCCs, were extracted using LibRosa. Finally, the MFCCs were normalized using Cepstral mean and variance normalization. The audio data underwent pre-processing to extract Mel Frequency Cepstral Coefficients, MFCCs, using the LibRosa Python library. Specifically, MFCCs were extracted from 124 milliseconds windows with a 92 milliseconds overlap, resulting in 15,420 total coefficients for every 8-second audio segment. This process is illustrated in Figure 4. To mitigate overfitting and data scarcity, the audio data was augmented through pitch shifting and noise injection strategies, increasing the sample size 7-fold. Pitch shifting involved adjusting the pitch by NN, NN, and NN semitones, while noise injection entailed overlaying a NumPy array with randomly assigned values onto the audio data. The extracted MFCCs were then normalized using Cepstral mean and variance normalization, CMVN, to account for additive noise and differences in recording conditions. CMVN normalizes the spectrum to have zero mean and unit variance, which has been shown to improve the performance of speech recognition algorithms. Visual pre-processing consisted of 2 stages: video segmentation and facial action unit, FAU, normalization. Video data was segmented to only include data from when the patient is speaking, using timestamps provided in the transcript. The data was then sliced into 8-second segments, aligning with the segmented audio data. FOW values were normalized to zero mean and unit variance, scaling continuous, non-discrete values. For text-based model development, a two-shot learning approach was employed using GPT-4 through the OpenAI API. The model was given a prompt to determine if the patient has depression based on full text transcripts from the DAIC-WOZ dataset. The prompt was modified from the one presented in Galaitzer-Lev et al. 47. The model was expected to output a binary classification of depressed or not depressed in JSON format. The facial action units, FAS, available in the DAIC-WOZ dataset, listed in Table IV, include 20 FAS, which were normalized for zero mean and unit variance. The cropped therapist audio was discarded, and the remaining audio data was separated into smaller chunks to make it suitable for input into bidirectional long short-term memory, BiLSTM, layers. The audio data was sliced into 8-second segments, where any remaining segment under 8 seconds was discarded. The proposed model architecture, optimized through hyperband tuning, is depicted in Figure 5, with the corresponding hyperparameters listed in Table V. This model consists of 3 consecutive blocks of BiLSTM, dropout, and batch normalization layers, followed by 4 dense layers. In the model development process, hyperband tuning was employed to optimize the architecture, using the atom optimizer and binary cross-entropy as the loss function, with class imbalance addressed by weighting the depressed class. The tuner focused on validation loss as the sole performance metric, and the number of total epochs and models tested was reduced by a factor of 3 in each bracket. A callback was created to terminate training and move on to the next configuration if validation loss did not improve over 3 consecutive epochs. 2 iterations of the full hyperband algorithm were run. Following hyperparameter tuning, the model parameters were reset, and the optimized architecture was evaluated using Leave One Subject Out cross-validation, LOSOCV, as visualized in Figure 6. In LOSOCV, the model was trained for each clinical interview in the dataset, excluding samples from one clinical interview, and the model results were pooled for the final performance calculation. Augmented samples were not included in the testing data. The proposed architecture, detailed in Section C, extracts higher-level features from the Mel Frequency Cepstral Coefficients, MFCCs, in 3 consecutive blocks, followed by processing steps to prepare the facial action unit, FAU, data for concatenation with the MFCC tensor. The FAU data is first flattened into a 1D tensor, then repeated for each time step present in the processed MFCC tensor using the Keras repeat vector layer. The proposed architecture's performance is evaluated using confusion matrices, as shown in Figure 7, on the AVEC 2016 cross-validation split and Leave One Subject Out cross-validation, LOSOCV. The results demonstrate the model's ability to accurately classify depression, achieving an accuracy of 92.85% on the AVEC 2016 cross-validation split and 90.22% on LOSOCV. A comparison with baseline binary depression classification models is presented in Table V, highlighting the proposed model's superior performance in terms of precision, recall, F1 score, and accuracy. Specifically, the model outperforms state-of-the-art models, achieving an F1 score of 78.79 and accuracy of 85.11. The proposed architecture's computational complexity is evaluated, demonstrating its ability to process a 12-minute 50-second clinical interview in 2.67 seconds, including GPT-4 computation time through the OpenAI API. This efficient processing time enables the deployment of the proposed architecture in a clinical setting. The model is integrated into a locally hosted web application, DEPScope, for easy and accessible use by clinicians. The application connects to clinicians' Zoom accounts, allowing for automatic processing of clinical interview recordings upon conclusion. This seamless integration enables clinicians to quickly and accurately assess depression in patients, facilitating timely interventions and improving patient outcomes. The proposed architecture's performance and deployment demonstrate its potential as a valuable tool for clinicians in the assessment and treatment of depression. The proposed architecture for diagnosing major depressive disorder, MDD, from clinical interview recordings achieves state-of-the-art performance, outperforming baseline and existing models. On the AVEC 2016 cross-validation split, the model achieves a precision of 92.86%, recall of 96.43%, F1 score of 68.42%, accuracy of 78.79%, and specificity of 85.11%. These results are further validated using the Leave One Speaker Out cross-validation (LOSOCV) technique, demonstrating the model's ability to generalize to unseen speakers with a precision of 80%, recall of 90.23%, F1 score of 92.86%, accuracy of 85.95%, and specificity of 91.01%. The interview collection and processing pipeline involve collecting audio recordings, pre-processing them using the DEPScope backend, and generating clinical reports via GPT-4. These reports provide a summary of the interview, including key points and justification for the diagnosis, along with the model's confidence in the classification. The novel Tri-Modal architecture integrates large language models and audiovisual features, optimized using automated hyperparameter tuning techniques. While the proposed architecture achieves high accuracy, its limitations include slow speed, making it unsuitable for real-time applications, and reliance on large language models. The dataset used, DAIC-WOZ, is small and homogeneous, which may have negatively impacted the model's generalizability. Future work aims to optimize the architecture for increased accuracy and accessibility, as well as explore new large language models to address the issue of limited high-quality data available for this task. Developing an accurate diagnostic tool for clinical depression and anxiety remains a pressing challenge. Current methods rely heavily on subjective psychiatric diagnoses and self-reported data, which are prone to social desirability bias. To address these limitations, researchers have turned to advanced machine learning techniques and multimodal data integration. By combining patient-reported symptoms, clinical interviews, and physiological measurements, the diagnostic accuracy of depression and anxiety can be significantly improved. The incorporation of large language models holds particular promise, enabling the development of more adaptable and performant models. This comprehensive approach involves the detection of vocal biomarkers for anxiety and depression through audio-based analysis, leveraging acoustic differences between healthy and depressed individuals. Additionally, identity-aware facial action unit detection provides further insights into emotional states. The proposed diagnostic tool integrates these modalities to provide a more accurate and nuanced understanding of depression and anxiety. By moving beyond reliance on self-reported data and subjective diagnoses, this approach has the potential to revolutionize the field of mental health diagnostics. The integration of multimodal data and advanced machine learning techniques offers a powerful tool for clinicians, enabling more effective diagnosis and treatment of these debilitating disorders. Unfortunately, it seems like the original content is missing. Please provide the original text, and I'll be happy to refine it according to the guidelines, transforming it into a concise, technically accurate summary suitable for voiceover narration.